It's okay, I'll figure out what to say. The less the better. I know. It's a very distinguished lecture. You gotta get it very elaborate.
The chair funding was, I don't know, just 5, 10. Max, you can have it. They could have 100. They could easily.
You don't know which one to
We're not in this area.
Where he's coming, he put money for that. Did he give a hint? Like, they already made their pick.
Do you have enough light to geography? Turn on the stage.
I don't think he has the money in giving out.
Just on this time, you have to do that? Why don't we? Okay, I'm going to go wrong. Okay, let me thank everyone for coming. It's my pleasure to introduce Professor John Bowers of UC Santa Barbara. And he has a distinguished career as an academic, and he has had many awards. And just to give you some idea, he received the IEEE Photonics Award, the Optical Society Tyndall Award, the Optical Society Holoniak Prize, the IEEE William Stryfer Award. But he is also a South Coast Business and Technology Entrepreneur of the Year. Now, you might find the South Coast, he must be from some other state. He can't possibly be from California. But actually, the southern part of California is actually facing south rather than west. Just check it out on a map. So that explains why he keeps getting these South Coast awards. Okay. Now, so this is all very good, but even more importantly, he is the co-founder of several successful companies, Orion, Arius Photonics, and Caliant Networks. So that's rather interesting. Now, the reason why he's here today is to tell us about this new national plan for silicon photonics. I guess it's called AIM, something to do with manufacturing. But it's really a plan which is a little bit odd. I have to tell you, I felt a little bit uncomfortable about the whole thing because I am the founder of Luxtera, which is a silicon photonics company, and we raised a lot of money. But for AIM, they raised $600 million, which is a lot more than we raised. Okay, and so what does the government have in mind? What are the plans? What's really going on? And what happens when the government makes a big commitment to business like this? And I'd like to find out about that. So for that,
600 million of government money.
it was all 600 million is government money.
No, it's not true.
Okay, then you'll explain. Okay. Okay, let's go welcome John Barrows. Big hand.
Thank you, Eli. So Eli picked this title, so I'm not entirely comfortable with it, to be honest. So I will attempt to address this title. But indeed, we'll talk about this new center. And in the end, I think the main way we change information technology is by affecting communication within data centers and ultimately communication on chips, so optical interconnects off electronic chips. But let's first start talk about this national center. If I can absolutely work this. Okay, so I'll talk about this. I'll talk about sort of where I think integrated photonics is going, and that's actually going to be controversial. Eli will not agree with what I'm going to say. But I have well, he has a microphone too, so I may be in trouble. But, so at any rate.
He's holding on to it a bit.
So indeed, it's called AIM, the American Institute for Manufacturing Integrated Photonics, and is actually established by President Obama. A lot of what this is about is themes that Trump is talking about, job creation and U.S. industry and things like that. So some of these slides will look like that, but this has actually been a big issue for President Obama. And so the goal is to create a National Institute for End-to-End Integrated Photonics in the U.S. So it's much more than just a multi-project wafer runs. It's packaging. It's a lot of EDA tools and things like that. So there's a whole bunch of these manufacturing institutes that President Obama set up. I hope they all survive. It's interesting to me that several of these actually were just in the last month were announced. So we've seen quickly how things can change in the new administration. But at any rate, we're back here. Established July 2015. It's DoD-led. Some of these are Department of Commerce, some are Department of Energy. But there's a whole national network. And the goal is to bring back manufacturing. And so this was the goal, again, as clear. We're facing a national deficit. A lot of technologies, a lot of manufacturing is being transferred overseas. And certainly in the photonics area, that's very, very true, right? In the 2000 downturn, a lot of photonics went to Asia and has never come back. And so that's the question: is can we turn this around and bring back lots of jobs in the United States? That's the main goal. So the point being that there's lots of in all these institutes, there's lots of products that these days actually don't have a lot of manpower involved, right? It's not that labor is cheaper in Asia matters. A lot of these things where there's displays or solar cells. Indeed, Eli manufactures solar cells in Silicon Valley. So, if it's automated, then hourly wage shouldn't be the issue. And so, if labor cost isn't the issue, how can we bring these technologies back? And that's the goal of these. The other general goal of all these is to basically fill this gap between government and universities and the private sector and this valley of death. And in particular, where we're supposed to be residing is in here. So manufacturing readiness levels of 4, 5, or 6. So I'll get into more specific about this in a second, but this is where many people have failed to engage very well, right? So we have call for proposals every year, and we're building up to the next call for proposals. And there's lots of groups that are getting funding, and a big issue is this is not supposed to be about what you could get NSF or DARPA or someone like that to fund. If you're over here in the research end, then that really is not of interest to this institute. And so you can do research and use all the facilities, but if you want to get funded from the institute, then you have to be basically pointing out how you're going to take something that's here and move it over here. And that's the basic goal for AIM. So this is the centroid of it. It's centered at SUNY. which is it's a fabulous facility. The state of New York has invested a lot of money. There's actually 4 or 5 buildings like this. It's an old IBM campus that have clean rooms in them, and they're large clean rooms, right? It's 1.3 million square feet. It's 135,000 square feet at Class 1. So this is way beyond anything we have at UCSB or you have at Berkeley. So it's all cassette-loaded, 12-inch silicon. It runs a 65 nanometer process, so most of the photonics is running that. They do make things as small as 7 nanometers, so they've made 7 nanometer transistors and written papers about it. But that's a facility. And our role at UCSB, well, we're ahead of the West Coast, so it's everything west of the Mississippi. And my main role and our role is to basically try and be an interface and help people get into using the facility. What we're actually doing for research is a few different things, but largely adding 3.5s to this process. So primarily MOCVD based. So SUNY has a 12-inch MOCVD reactor, and we're transferring technologies to grow 3.5 and silicon for optic devices there. And then they're going to grow them, and eventually the idea is to integrate lasers with the rest of this. And so that's our goal. Right now, most of the good results are coming out of MBE more than MOCVD, so that's an issue because at this point they haven't bought one, but 12-inch MBE reactors exist, and they'll commit to that. So again, they have a lot of funding to really make things happen. So in answer to the earlier question, they get 110. AIM gets $110 million over 5 years from the Department of Defense. And then the state of New York has committed $250 million. And that actually is real. That's cash they've invested into this. And in some cases, it's to upgrade the facilities here to do silicon photonics. Other cases, it's to build a complete packaging line. So there's a new building that's rented with an existing clean room in it. And this year, they'll spend about $50 million buying a complete packaging line so we can package all these devices. So that only adds up to $360 million. And the rest then is some from the state of Massachusetts, state of Arizona, state of California, and then most of it is from industry. So typical Tier 1 membership is $1 million per year. So typical Tier 1 members put in $5 million. And so that's where the balance comes. That gets up to over $500 million. So if there's any questions, I would say ask them now or as we go along throughout this talk. There's multi-project wafer runs. You can download the PDK from Moses, and that's just gotten set up. There were 2 multi-project runs in 2016. There'll be 3 this year. The next deadline is February 28th. And obviously, to get through all the design rule checking and things, one needs to be submitting this and being sort of in line a lot sooner, as well as just reserving space, like any multi-project wafer run. And then there are 3 interposer runs. So these are, again, they're like a multi-project wafer run, but they're just waveguides and then lasers that are flip chip bonded onto there. So right now, 1310 lasers and soon 1550 lasers. So again, if you have a silicon photonic chip, today, without any lasers, you can mount that onto an interposer and then have some array of lasers on that. So that's the way we get light into these chips. I hesitate to even show this slide, but this is how it's organized. So in detail, Mike Watts is the Chief Technology Officer, so he has a lot to say in terms of what things get funded, what things happen. And he's nominally over all of these groups. So these are the different application areas we've chosen to focus on. So datacom, telecom is a big effort. By far, that's where most of the industrial members are working. So certainly, Intel, Infinera, Cisco, HP, IBM, that's their primary focus. There's a group on analog, and that's primarily the government, but it's also companies like Infinera and Keysight as 2 examples of companies well involved there. There's a PIC sensor area, and again, there's a lot of little companies that do lab on a chip, photonic integration. The big player right there right now is GE, which has a big suite of sensors that they're running through this foundry. And then the last one is it's called PIC array technologies. I guess I would think of it somewhat as either free space communications with steered beams or LiDAR applications. And obviously optical LiDAR is a big thing. So those are the main application areas. And so those projects in those areas get funded. Most universities are probably sitting there. These are the technology areas. And so a big area is electronic photonic design automation. And that's what Vladimir here gets funded on at Berkeley to do basically a reference design for 25 gigabit analog, datacom applications. There's a lot of work on improving the multi-project wafer work. So our work on laser integration into this process falls under there. So that's not something they offer in today's PDK, but our goal is certainly maybe a year from now to have integrated lasers on that platform. A lot of it's on test assembly and packaging. So again, the $50 million on building this packaging facility in Rochester, which should be a very modern optical packaging capability, unlike, again, most universities or most small companies would have, falls under there. And then there's this last one of inline control and test. So again, working with companies like TEL to get high-speed inline testing. So this cartoon here is supposed to indicate they're all supposed to work together and talk to each other like any matrix organization in a company. I'm not sure that happens. I won't go into this in detail, but these are just a little more detail of what I just ran through of some of the projects and areas that are going on in each of those. And same thing with the technology areas. So I'll leave these slides. But again, there's a website. All of these things are on the website, so you can find this in more detail. So in each of these cases, there will be new additions. There's a call for proposals every year, and we're not limited to those 4. 3 of those 4 were required in the original call from the government, and then the 4th one down here we added as something that was of interest to us.
Can you tell us a little bit about the politics of this? How did you get New York State to commit $250 million, for example?
Well, they very much wanted to be. They had actually bid several of these and had not won any of them. So this is a big, clean room facility. And so the previous one to this was the gallium nitride consortium, which they actually committed $250 million to and didn't win. So they committed the same amount of money to this one and did win. It came down in the end, initially they had lots of proposals, and then it came down to 3 that they had site visits for, and this is the one that was chosen. I think by far this had the strongest technology. So if you're going to fund a foundry, this was by far the strongest. Now they want to do much more than a foundry, right? So I think all the EDA companies were involved in every center that hit the finals. So I don't know that they were a differentiating factor on that. But that's a big part of what people want out of here, is that there are great EDA tools. There aren't great photonic tools. And so that's a big focus in the center. These are the members right now. It's a little out of date.
By the way, you've used the acronym PDK several times.
Yes.
And so maybe it's good to define it.
So yeah, Photonic Design Kit. Thank you. And then, so yeah, if you download this Photonic Design Kit, it's currently version 1.0. It first went up last August for the run that was in September, and that was 0.5. And again, there's a lot of automated data taking going on, a lot of calibration of models, and the goal is that this is a solid design kit that actually meets what it says. I think that's true. I mean, from the first run, frankly, there were some aspects that things didn't come out where we were hoping they would in terms of like doping levels, say. But most of the specs that are in that design kit are derated substantially. So as a result of that, the modulators were not as fast as we were expecting, but actually they were as fast as they were quoting. So this is certainly a technology you can make 10 gigahertz modulators in, but we're actually looking to do 25 to 50 gigahertz out of this technology. So, I would say the performance specs in that design kit are derated substantially, including losses for things and things like that. I would say the uniformity across the wafer is strikingly good. I mean, compared to what we see at UCSB with our smaller tool set, If you take the 3.5 growth on 12-inch silicon, the uniformity across that is remarkably good, and the quality variation, say, of X-ray line width or PL capability is very small across that. So it bodes well. I'm impressed.
Can you explain that? How do you grow gallium arsenide on silicon?
I'll have a bit on that at the end, but initially, our initial results use a germanium initial layer, and then we grow gallium arsenide on that, and then say indium phosphide, and then quantum dots on that. And I'll go into why. More recently, what's working really well is to grow on 111 surfaces. So it's say a 100 nanometer, 200 nanometer period V grooves, and then all of the stacking and dislocations come up on the 111 faces. But if you have a little piece at the top underneath for the oxide to etch the V groove, that ends up trapping all these dislocations. And so you can get remarkably lower dislocation density in an active region then. And so there's a bunch of different approaches. So one approach is to initially grow a very thin 5 nanometer aluminum arsenide and then gallium arsenide. We're currently most happy with the gallium phosphide approach, and then we're growing on top of that. But I'll show those results at the end. So this is Infinera's slide, and so they're probably the premier, well, Luxtera and Infinera, but these guys have been doing integrated photonics in volume for quite a while. And obviously their first products were 100 gigabit and then 500 gigabit. Now they've got a 2.2 terabit chip they've demonstrated, and they're looking to go beyond that, 4 terabits and beyond. But they're a key player in this, and they are developing indium phosphide PDK. So everything I've talked about at the beginning and going forward will pretty much be silicon-based, but this is the indium phosphide base. So that's their interest, is taking telecom and datacom expertise and applying it in particular to microwave photonics. So this part is controversial, and Eli will disagree with this. I'll go through sort of 4 generations I see of integrated photonics. So I think the first generation was certainly Infinera or indium phosphide based. So I mean, there's certainly a lot of work at Bell Labs and photonic integration back in the late 80s and throughout the 90s. These guys started about 10 years later, but Lumentum, Finisar, and there's a bunch of companies, right? That's where the bulk of photonics is done today. So if you look at where most transceivers come from, it comes from those companies. So that was the first generation, and Infinera represents that. The second generation is what I would call silicon photonics. So again, it's silicon on an insulator, and so there's a bunch of foundries that do this, AIM being one example, but IMEC, IME, Freescale, ST, and lots of companies. And so Luxtera, Cisco, Acacia, and these are all shipping significant volumes of products for the datacom and telecom industries. So why use silicon? Why might silicon replace indium phosphide? Well, a lot of the issues here, right? So all of these foundries are running 12-inch silicon with really good process controls and good uniformity across there, and very good lithography, right? So 65 nanometers in the case of AIM. A lot of other ones aren't necessarily at that level, but that's much better than the lithography tools that exist for small wafers, right? And the problem with taking 3.5s to larger than, say, 3 inches or maybe 4 inches is several-fold. One is it's very expensive. 6-inch indium phosphide wafer is $7,000. That's prohibitively expensive. But even 2 and 3 inches is a substantial cost. The other issues are just fragility, putting them in automated wafer handlers. And so the real goal of most of the companies is by getting to a 12-inch, using modern process tools, modern test tools that exist at 12-inch that didn't exist back when people had smaller wafers, and modern packaging tools. So again, the most advanced silicon photonics companies are all using high volume, auto-tested structures on this. So that's kind of the big motivation: wafer scale testing, wafer scale packaging. And as you start getting up to higher data rates, that starts to become important because these chips start to become large. So some things like the LiDAR chip, that's a fairly big chip. Several terabit transceiver, that's a fairly big chip. It's not just a laser you put in a little can anymore. And the ultimate driver is integrating this with electronics. And that's, in terms of the title I had, that's really where the impact comes, right? When every processor, every memory now has photonics integrated in the same silicon foundry, and that's the big driver. And if you talk to Google or any of the switch companies, they all see that limit today. They all argue that they can build bigger switches than they get the I/O on and off of. And so that's where photonics comes in. And so we're seeing the first beginnings of that. You know, today, just about every router and most systems, transmission systems, they have a circuit board, and all the photonics is in a package around the edge. But now, you know, everything is going mid-board optics because there's too much attenuation at the higher data rates to get to the edge of the board. And eventually, that'll move inside the package itself. And so that's the real driver, I think, for silicon photonics, some 2.5D or 3D integration of the photonics and the electronics. So this is an Intel slide, but it summarizes, again, why do silicon photonics. And this will be really the next generation, but the goal, Intel's goal in particular, is to integrate lasers with all the advantages of silicon manufacturing. And this part, I think, is true. If you look at where Lumentum is today, you know, their wafer sizes are smaller than this, actually, and the lithography is down here. So many companies, if you want to do a DFB grading, use holography because they don't have the lithographic tools to write a 130 nanometer line. But if you look at what Intel's doing at 300 millimeters, they're writing arrays of DFBs with different grading pitch. It's just in the CMOS design. And so again, that jumping 6 generations is the real value of going to silicon. So these are the companies that do silicon photonics. There's a lot of companies over here on the left-hand side that are really focused just on silicon photonics. Some of those have gone away as these players have decided they need to own some of that technology. But Intel is certainly a big player. Juniper bought Orion, they're a big player. Cisco bought a company. HP has a major effort, and so forth. Huawei's bought a silicon photonics company. Melonix bought a silicon photonics company. So a lot of these, we're seeing consolidation happen at any rate. The good news for everyone at all the students here is there's lots of foundries that exist. And so obviously I've been talking about AIM in particular, but Leti, IMEC, Lyonix, not so much IBM anymore, but Moses, Global Foundries, ST, all run our foundries one can use to do silicon photonics. Not all of them run multi-project wafers, though. So in terms of the field, I'm amazed that it continues to grow. So, Richard Soref wrote the original paper in '87 about using silicon as an optical material, and nothing happened for a long time. It wasn't really until around 2005 that things took off, but it continues to grow. So, there's annually, now about 3,500 papers written on a silicon photonic topic, which is kind of a problem because it's a lot of papers to review. So I'm sure Connie gets lots and lots of these to review, and that's painful. But so a couple just comments again for people who aren't in the field. Why use silicon? So if you look at indium phosphide and infinite process, the waveguide has an index of say 3.5. The cladding has an index of 3.3. So it's 0.2 index difference, and that's pretty minimal. So you can't make sharp bends, but in silicon, index 3.5 to 1.5, you can make very sharp bends, and the bend loss is extraordinarily small, right? So even for a 6 micron radius bend, a few thousandths of a dB per turn. So you can make arrays of rings, and there's lots of interesting filters and things that one can do, and so it works really well. And again, here's some of the different things that people make. These are typically heaters for ring resonators. But again, the good process control in silicon photonics makes that all possible. Some of the devices we've been working on, for instance, are passive devices, are polarization beam splitters or polarization rotators and splitters. And the performance depends very much on details of the width, right? So the curvature here matters, the gap matters. A lot of times the gap is changing along the length, the width is changing along the length, so as to get the property you want. And the nice thing about these 65 nanometer technologies is it's pretty reproducible, and you can design something and get something. At UCSB, we have a hard time with something like this, that clearing that small gap in there reproducibly the same depth all of the time is a problem. But that's just one example of some of the passive devices that are being made. So Eli is the founder of Luxtera. They really started one of the first silicon photonic companies that got started, and they've gone through a bunch of different technologies. This is particularly successful. So PSM4 transceiver, shipping in volumes, millions sorts of numbers, not tens or hundreds or thousands. So again, that's what the chip looks like, and this is kind of where technology is today. You mount it in a package with the electronics. You have to keep that below 3.5 watts total power. So the laser and loss of this optical package matters a lot. We'll get into that a little more later. This just shows, again, some of the technology. So originally on 200 millimeter, now on 300 millimeter at ST. And this will now transition into the next one. So this is how do you get light into that silicon photonics chip. Right now for AIM, it's a flip chip laser going into a silicon waveguide to a flip chip photonic wafer. In their case, there's a laser sitting up here, and a ball lens, and an isolator, and that couples down to a grating coupler into the silicon photonic structure, and you can see these things here. It works. It's in high volume production, and Eli would argue that the cost of making this package is not significant, and is not the limiting issue. I would argue that there's a next generation beyond that, and that's where we'll get to in terms of integrating that laser on chip. In terms of active devices, most of these silicon photonics, up to what I've talked about, are all using germanium detectors and germanium modulators. And this is one example of what IMEX process is, but all the major players have it. It all works well at 25 gigabit. And I think we'll go certainly to 50 gigabit. One can use germanium to integrate the laser onto that chip. The problem with that is that the threshold for that is very high. So again, it may not be calibrated, but 300 kiloamp per square centimeter is 1,000 times higher than where we are today with epitaxial growth on silicon, or more than 1,000 times higher than where Infinera and Lumentum are with an indium phosphide laser. So it just doesn't play. It doesn't work because in these transceivers, power is the big issue. And the total power budget has to be 3.5 watts, say, for one of those packages I showed. And that means the laser thresholds have to be down 10 or 20 milliamps, not, amps.
So for the 3.5 watts, what's the data rate
Say 100 gigabit transceiver. So it could either be a 4 by 25 PSM4 in parallel, or it could be 4 wavelengths. And I'll show some examples of both. So my comment there is just that germanium detectors and modulators work really well. Germanium lasers don't work until you get to the point that it's direct bandgap. So if you look here, this is work out of MIT. If you get enough strain in this material, you can make it direct bandgap. And if you make it direct bandgap, then it can be efficient. But it's not surprising that an indirect bandgap, everybody's still back here somewhere, is not very efficient and really isn't credible for use yet. So do you need an on-chip laser? That's a very valid question. So Luxtera has a laser off chip. I'll show examples of transceivers where we now have, say, 64 lasers on a transceiver. That becomes pretty painful to have 64 for every die. And that's where it starts to become interesting. So you can analyze a couple different cases of having a laser off chip versus having a laser on chip. And indeed, the on chip one I'll show experimental examples for are with DFB lasers and arrays of them to make a WDM network. And the reason I'm making this point here is that a lot of people say, well, light is just a utility. It's just like putting a power supply on there. You put 5 volts on your chip. It's very different, right? When you put 5 volts on your IC, those are electrons. Those are, fermions. They stay on a capacitor. You turn off the transistor, they sit there. They're not flowing. The problem with photons is bosons. They move at the speed of light. So, if you have this off-chip laser, it's distributing its light onto that chip. Even if you turn all the modulators off and absorb that light, the photons don't sit there on a capacitor. So it's not like a power supply at all. That's, I think, a very poor analogy in my opinion. So it turns out if you analyze this for different cases, take some energy efficient processing scheme, and there's two examples here, crossbar butterfly architecture. What do you gain by having the laser on chip versus off chip? It's somewhere between a factor of 100 and a factor of around, say, 6 or 7. So if you've got a multi-core architecture and the lasers are on, every core is on all of the time, you don't gain as much. But if you're turning off 3/4 of those cores, as one would do in some proportional computing scenario, then you actually save a lot. You save up here. And so some of it's the coupling from the laser onto the silicon chip. Some of it's from the fact that you can turn off 3/4 of the lasers and not use them. Some of it's because you can intelligently place the lasers where you'd like to. So rather than have some tree architecture from an off-chip fiber, you put the lasers where you'd like to have them and don't have all the distribution losses. So you gain a lot. Power is a big issue in all of these structures. So I would argue that the third generation of structures is having integrated light sources on the silicon photonics. And the main way that's being done is with heterogeneous integration. So again, it's not unlike work that Eli's done in the past on transferring films onto substrates. These are all pretty much taking wafers and bonding them onto silicon and then removing the substrate. And there's a number of companies that do that, particularly Intel and Juniper. So this is the work Alex Fung did for his thesis, and just an example. So you have waveguides in silicon. So again, the silicon waveguide loss is lower than indium phosphide or gallium arsenide. And part of the mode extends up into the 3-5 layer where we can have quantum wells and get gain or absorption or modulation or detection out of those structures. And so here's just a picture. This is actually every third laser. There's actually 21 lasers here, but we probed every third laser just to give an example of laser integration. So that's the general process. Most companies put down pieces of 3-5, and there's two reasons to do this. One is that the cost of the 3-5 is a significant part of the total cost. So as you'll see in some later examples where you can see the individual photonic structures, the regions where you need gain, lasing, is pretty small. Most of it's taken up by things like WDM combiners and demultiplexers. So this is an example of where you're putting these materials down, sort of 25% of the area. That cuts the cost down by a factor of 4. So if you look at what Juniper does or Intel does, they're typically bonding 4,000 or 5,000 of those pieces at one time, all at once, and it's all processed together. So we're not mounting lasers one at a time, but you're mounting pieces of material and then doing all the processing. And that's what this is indicating down here. You mount these pieces, you remove the substrate, and then you process them. And one thing you can do here that you have never been able to do before is these might be different materials. So if you look at a typical Juniper chip, there's 3 different epis on every die. And so there's a laser epi, there's a modulator epi, and there's a detector epi. And if you look at what Infinera has to do for that, they have to do, in the end, they do 6 regrowths in their process. So they take an indium phosphide wafer, they grow the active region, they etch it away, they grow a modulator region, they etch it away, they grow a detector region, they etch that away and get some insulating regions. So lots of regrowths are expensive and they really affect your yield. This is a way to combine multiple epis together, and that's one real advantage of this general approach. So this is some of the work we've done just to indicate you can combine more than just different functions like lasing, modulating, detecting. This is, we've gone as short as 1 micron, but one can certainly go into the visible, mount 780 material or 870 material or 980 nanometer material. Obviously, silicon's absorbing, so you have to couple those lasers to silicon nitride waveguides, and that's what we've done. Most of our work has been at 1.3 and 1.5 microns, and those work, up to 100 degrees, and they put out, tens of milliwatts of power. But one can go to longer wavelengths. You can go to 2 microns, or even go to 4.6 microns and make quantum cascade lasers. And so again, those are for sensing applications is the big application. So here's just an example of it. Looks just like the picture I showed before. There's a SOI material here, but typically now you need to get rid of the silicon dioxide. So it's a SONOI process. It's silicon nitride, so as to keep the lower oxide away from the mode. But this is what it looks like for a quantum cascade laser. And you can get hundreds of milliwatts out of these structures. And you can make DFB lasers, which is what this is. So 2 DFBs at different periods. So it can work pretty well even at longer wavelengths. One can bond other things besides gallium arsenide materials or indium phosphide materials. You can bond lithium niobate and make doublers. There's a number of universities and industries now doing that. You can mount YIG on here to make isolators and circulators. So we've made 4-port and 6-port circulators. And you can integrate with nitride waveguides. So Intel is doing this seriously. And they run this on, all run on 300 millimeter platform. So again, this is one of their slides, just talking about basically making transceivers that are, in this case, this is 4 by 25 gigabits. So each channel is 25 gigabits. And again, their focus is, all automated processing and then high volume testing and high volume packaging. So again, if the Intel CTO, when he presented this a couple years ago, talked about their testing rates were something like more than an order of magnitude faster than anyone in the industry had done up to that point. So again, like they'd approach testing anything. So here are their 2 first products. One is the PSM4, similar to the Luxtera product we showed, and the other is the CWDM4. So again, this is 4 wavelengths, coarse WDM space, 20 nanometer spacing. But again, in one of these same little packages. So that's where it is today, and everyone's moving more towards midboard optics. So these will be smaller things which are not pluggable on the side, but getting closer to the silicon processor or silicon memory or silicon switch chip. This is the work out of originally Orion, now bought by Juniper. So looking at, again, in this case, at routing applications. Cisco is doing similar things. Oracle's doing similar things for routers and switches. Melonix is doing the same thing for switches, of using silicon photonics to get light into their electronic switching platforms. So again, this is a picture of one of their wafers. So you can't see the little bonded devices anymore, right? The substrates are moved. It's just a micron thick 3.5 layer, and all the rest of the processing goes on. It gets packaged in a BGA package. So again, looks different than most of the industry, right? So if you look at most Lumentum products, they're gold boxes with a ferrule and fiber coming out. These are typically BGA packages with, again, snapped fiber connection to it. Most of this, by the way, is not hermetically sealed, and that's a big change. And that, I didn't sort of point that out earlier, but the big problem in indium phosphide or gallium arsenide lasers is facet degradation. And that's where most defects start and propagate in and kill the lifetime, and often require hermetic packaging. In this case, all that's exposed to the air is a silicon waveguide. The 3.5 is completely buried in an SiO2 layer that's fairly thick. So there's no need typically to hermetically seal these devices. So this is just another example. They have a 4 by 25 gigabit WDM package, and it just shows 4 eye diagrams, and that it works. So that's sort of where it is today, and as I keep saying, where we're headed, I think, is something like this. So it may be a memory with multiple 3D bonded silicon layers, or it may be a processor with again, a photonic layer underneath, and then some sort of silicon interposer or silicon substrate. But basically, the connection between these electronic chips is now optical. So we need to do 3D bonding of these structures. So again, that's something that AIM can do today, and they're offering this. Vladimir, in particular, has been bonding ASICs to silicon photonic chips on some circuit board. And so that is a standard process that AIM is offering on a 300 millimeter scale. So that's where we want to get to. As a first step there, obviously there's lots of electronics today that has multi-cores, right? And so indeed, 500 cores, if you figure out how much data that is, that's a lot, right? If you have 200 data lines, 5 gigahertz, that's a terabit per core. 500 cores, that's a 500 terabit network on that chip. So that's where the value of photonics really comes in terms of efficiently utilizing those cores. So we've looked at that, and this is a chip we built recently. So again, it's network on a chip. So the intent is we connect to 8 different cores on here. And each of these then has 8 DFB lasers, 8 modulators, 8 detectors. And then you can see what the chip looks like here. These are the arrayed waveguide routers to do the wavelength combining and splitting. And there'll be a better picture here. So this is the output, say, of one of those 8 transmitters. And so there's this AWG, which has its performance here. It's actually really quite good. Loss is less than a dB. But there's a DFB, and each one now has a different grading period. So again, with CMOS, you can write those periods. And each one is slightly different, right? So it's at a different wavelength. And the modulators. And if you look at the chip, you know, most of the area are these things, right? These are the AWG multiplexers are the big pieces. The DFB lasers, those are 8 DFB lasers across there, are really quite small, and you can put them quite close together. So that's one example of where that is, that technology. Again, Berkeley's way ahead of where we are in terms of electronic design tools, and again, in AIM in particular, working very hard to get good photonic design tools here. So here's a few examples. This is some work that we've been doing with modeling of our lasers. So again, these are heterogeneous lasers with the tools. Again, IV is pretty easy to model. And then these are the individual modulators, again, either modeled in cadence or lumerical or synopsis. So we work with all 3. And then this is the overall modulation response of that system. And the interesting thing is here, there's vague agreement between here, but the limit here in bandwidth is more than anything limited by the AWG. So that AWG, you've got to put channels every 200 gigahertz.
Acronym alert.
Oh, sorry, arrayed waveguide router. It's our wavelength combiner. Thank you. So it's, well, I don't have a picture here, but it's.
There in the middle.
Oh, is there a picture in the middle of? Well, the performance is here, but yeah, it's a splitter and then some number of waveguides of different lengths and then a combiner.
Losing.
Pardon?
It's losing.
Oh yeah, you're right. Okay, you can see it there. So you put in light from the laser here, and different delay lines across here. They all get combined, and then out of each of these ports comes a different wavelength. So on a DMUX, you have a different detector for each channel here. Going back. So this spacing is quite close, just a few hundred gigahertz. And so if we have 2 sidebands, each taking, say, 50 gigahertz, there's not much room in there for any roll-off in that performance. And you can see here, this is not a flat-top AWG. Now, other people designed flatter tops AWGs, which would work better. But for what we have here, that ends up being a limit. And one real value of these design tools is we can look theoretically at putting that AWG in or taking it out, or looking at different designs. And a lot of this roll-off in response is due to that AWG. So over here is the overall eye diagram, simulated and measured. And obviously, the simulation doesn't include noise. And this eye, frankly, is not very open, but we were able to get low error rates with it. So that's what I'm calling 3rd generation. And I'd suggest perhaps there's a 4th generation. And in this case, not just Eli, but Intel and others wouldn't agree with this. Although we actually work closely with Intel on this, is epitaxial growth of 3.5 in silicon. The main reason for that now is we get away from bonding individual chiplets. We get away from having to do epitaxial growth on expensive substrates. So it is the lowest cost approach. We don't have the advantage now of being able to bond different chiplets adjacent to each other. We've got to do regrowths like Infinera does today. So you save a lot on wafer cost. We're using quantum dots. So the advantage of quantum dots is lower threshold and high power, as you'll see. And that's, again, the big advantage of quantum dots is that they reduce the threshold. They reduce surface recombination, and that's important. So HP in particular is making very small devices, and the surface recombination of those would be much worse if they weren't using quantum dots. So their approach is entirely using quantum dots. You also reduce reflection sensitivity. So again, that Luxtera module you saw had an isolator in there. Okay, why does anybody else need an isolator? Well, if you have a quantum dot, it should be significantly less sensitive, which isn't obvious, but I'll show why in a second. And then the final reason is to improve the degradation. So again, when you grow 3.5 in silicon, it's not lattice matched. There's large dislocation densities, and dark line defect growth during that is a big problem. So quantum dots gain you immediately about a factor of 10. You get 10 times better lifetime by using quantum dots rather than quantum wells. But it's not yet adequate. So these first three are all viable approaches. They're all competing in the marketplace. This last one is not ready for prime time yet. So again, here's just a summary. We are actually getting wafers with gallium arsenide growing on it from AIM at this point. But that's an example of one of the 300 millimeter wafers. But the substrate cost for gallium arsenide is about $1 per square centimeter, $1.60. Indium phosphide is about $4.50. Silicon is 20 cents per square centimeter, right? That's a big advantage. SOI is more expensive, but maybe we don't use SOI. Maybe we do everything in 3.5. That's also very heretical to say, but might be true. This is the reason we're using quantum dots. So when you grow gallium arsenide on silicon, there's some dislocation density due to that lattice mismatch. As you go further up, the dislocation density drops. If you put strained superlattice layers and things, you can reduce that. But the problem is that the dislocation density is typically 10 to the 8th per square centimeter, which means there's a dislocation every micron. And the problem is the diffusion length in the quantum well is a micron. So basically the whole material is black. Everything gets recombined in dislocations. But if you can put a high density of quantum dots in there, we put about 500 dots per dislocation. So 510 to the 10 density. Then indeed a few of them have degradation, but only 1 in 500 sees that. This high dot density is also why the diffusion length is a lot lower, because carriers in here tend to see a dot and fall into that dot. Rather, if they're up here, they fall down into this layer and get trapped. So if this is a surface with a surface recombination, then only the dots very close to that surface see it. So the diffusion length is shorter, and we see lower threshold for small devices. So that's why HP is able to build 5 micron rings, and we've made devices that are actually 1 micron ring diameter, 1 micron diameter in the ring. So you couldn't do that otherwise. So this is sort of where that field has come. Back in '95, University of Michigan in particular, Bhattacharya's group started growing these structures, and threshold currents were high. Those are 4 kiloamp per square centimeter. This is where it is now, down below 100 amp per square centimeter. So that's better than a good quantum well laser. So this is all on silicon. So that's pretty good. The red here is on this axis. The red dots is the maximum CW temperature. So again, in the early days, they wouldn't even run at room temperature. Now CW, you can get them running up to 120 degrees C. So that's probably adequate for almost any application. Obviously, silicon electronics is going to run at certainly 80, 100 degrees C. This is marginal, but the highest temperature lasers are all quantum dot lasers. And so that's the focus. So this is the evolution. So there's been a lot of great work here out of Connie Chang's group on growing 3.5s on silicon, growing ribbons up and making lasers out of it. These are all in-plane structures. So again, going back to early work, everybody grows off-cut, right? Because you're growing a polar material on a non-polar substrate. So you've got stacking faults, lots of issues. If you grow it off-cut, there's distinct improvement in the performance. And so if you go back to, say, here, this is off-cut, 6-degree off-cut, and then growing germanium. So it's 6-degree off-cut SOI, then grow germanium. You can get good lasers, 120 degrees C operation, low threshold, 16 milliamps. But there's two issues here. One is there's this germanium layer, and the other is that it's off angle, and that's not a standard SOI wafer. It's not cheap and not readily integrable with the rest of electronics. So recent work has been going on axis, and there's several approaches that work, and you can now get pretty good thermal performance, pretty good thresholds. Not as good as this, but I think it will be soon. So it's looking pretty good. So this is the earlier work. These are grown off-cut on germanium, but again, just showing example of 12-inch growth. These are what the lasers look like. You don't see defects, morphological problems, but you can get 180 milliwatts CW out of these structures. That's not on a heat sink. And that's one advantage of silicon, which is silicon is very thermally conductive, twice as conductive as indium phosphide. The way to get on axis is to grow on V-groove structures. So now the silicon layer is on axis rather than tilted, but everything is 1-1-1 surfaces. And the reason that works, you can't really see it too well here, I don't think, at least I can't see it here, is that the stacking faults and dislocations propagate up along these 1-1-1 faces and typically terminate at this point. And so the dislocation density down here, stacking fault density is very high, but up here it can be quite low. And so the results I'll show here in a second are about 10 to the 8th per square centimeter. But we now have structures about 10 to the 7 per square centimeter. So our hope is with 10 times better, lower dislocation density that we can get better results. So the most recent work involves using gallium phosphide buffers. So in terms of the first thing on top of the silicon is a gallium phosphide buffer. And Larry Lee grew that, who's now at Illinois. But again, here's a bunch of the structures. These are some of the laser results. So they're not as good as before, but again, you can make reasonable lasers, putting out 10 milliwatts and highly single mode behavior. So the last issue is the sensitivity to reflection. So I just want to talk about that. So again, this is the Luxtera picture. You see the same thing from Cisco and other companies as well. But there's typically this isolator. It's pretty big. It's kind of expensive. It's in bulk. There's loss associated with it. And the question is, can we get rid of it completely? And it turns out people have been predicting that quantum dots should be better than quantum wells in terms of being insensitive to reflections. And so the critical power written here depends upon the K factor, this dynamic relaxation factor, damping factor, and it depends upon the line width enhancement factor. And so both of those should be better for quantum dots than for quantum wells. So if you compare, the blue curve here is for a quantum dot laser, the red curve here is for quantum well, you should gain from the K factor improvement, and you should also gain from the lower line width enhancement factor. So this would show an improvement of, say, 15 dB, if that were the value changes. So we did a comparison. So these are all quantum well lasers on silicon, quantum dot lasers on silicon. They're not perfectly equivalent, but they're not too far off. And so what you see here, this is a quantum well laser on silicon. And so this is the RIN and the relative intensity noise of the laser. And up to some level of feedback, about 1 part in 1,000, everything's OK. But then things get bad in a hurry. So lasers becoming sensitive to reflections. There's noise. It's not usable. You need an isolator if you're going to be in this region. And these are the results for quantum dots. So if you pick 135 as the magic level, then we're out here at about minus 10 dBm rather than minus 30 dBm as we get here. So there may be an improvement there. I'm not saying you have to have isolators in every product, but this is one reason to use quantum dots rather than quantum wells. So just to summarize what you can see with quantum dot growth on silicon, reasonable thresholds, not as low as we'd like to see, reasonable powers, fairly good temperature dependence, T0s of 100 degrees. And again, I didn't talk about these quantum dots. They're all grown by strained indium arsenide on gallium arsenide or on indium phosphide. And people are doing both for work at 1.3 or 1.5. This is where the field is now. So the blue is all of the best integration results on indium phosphide. And a bunch of these data points are Infinera, but certainly the highest one here, that's our 2.2 terabit per second transceiver. The red dots here are the biggest level of integration. So this is number of devices integrated on one waveguide. You can always have parallel waveguides and get more numbers, but these are numbers integrated on one waveguide. And so MIT is actually highest. This is Mike Watt's work on his LiDAR chip. But several thousand devices, and actually higher than the biggest indium phosphide chip. The green triangles are the results from integrating lasers on silicon photonics. And so this is our 2.5 terabit chip here, but it's about 400 devices or 440 devices integrated together. So that's our version of Moore's law of where the field sits. So I just want to thank all the students and postdocs and visitors who did this work. Obviously, I just come and give talks. But the point being that silicon photonics is here. So Intel has it on 12-inch. Acacia has it for telecom devices. It's kind of surprising, right? Acacia's market cap is very similar to, Lumentum or within a factor 2 of Finisar, higher than Infinera, actually. So Acacia is, again, a pure silicon photonics company that outsources all its silicon photonics fab. That's the value of it. And then Juniper Networks, Melonix, and others. So lasers on silicon are here. It's progressing. Epitaxial is not ready yet. And this is kind of sort of where everything stands. So thank you. I hope you have questions.